Hello, everybody. Unfortunately, I wasn't able to be with you today, so I decided to record the lecture. As a start, I'm going to continue with the solution of example 1, where we are given a beam that has four bars. It has the dimensions that are given on this figure, and we're asked to find the design strength. So the beam has no shear reinforcement, so we started with that. And we saw that AV being 0 takes us to the case of AV being smaller than the minimum shear reinforcement. So we ended up with this relationship for the design strength. It has two terms. We started with the second term. The second term is kind of easier to work with. We submitted all the values. We found a value of 8.75 kips for the second term. Then we went to the first term that has a little bit of more work there. We worked out all the terms, particular emphasis on rho W, which is the longitudinal reinforcement ratio, and lambda S, which is essentially the size effect reduction factor. We calculated those, and eventually we ended up with a strength VC of 15.129 kips. Now, taking all those into account, let's see what we have. We have our overall, just right here. Our overall shear strength to be CVEN equals the minimum of phi VC eventually, and the second term, this right here, second term. And what we have here, we have 0.75, the strength reduction factor times 15.129, and the second term includes 8.75 kips. Out. So out of the two, the second term is the one that controls, so we have 8.75 kips. So that would be your design strength for this beam. And that was the first step. The second step in this problem was to find essentially the capacity or the maximum load WU that it can be supported by this beam. So let's see what we have here for the second step. We have a simply supported beam. Okay, we have some applied load WU. Let me just apply this load. That would be WU. And because of that, you have a shear force diagram. You try to find what would be the maximum WU, that the ultimate W, in other words, that can be supported by this beam that has only some longitudinal reinforcement and no shear reinforcement. And the idea there is to set the demand equal to the capacity. So let me just go back here and write in what you need to find also WU. That would be what? And here probably I use question mark. So I go back down here and let's see what we have. We have the length of this beam to be 10 feet. So let me also write this to be 10 feet here. And we need to draw our shear force diagram. Let me just also draw a line at mid-span. So let's say that would be my V of X. And when I draw this shear force diagram, I would have a line that it would look like this. Just draw this line. Okay, and And this maximum value really here would be a negative W U L over 2. And this value over here would be W U L over 2. And now the question is that your design demand diagram? No, because your critical section will be at a distance D from the support. So we need to find essentially some distance D, the distance D from here. So this is D. We go back here and we found actually a slightly lower strength. So we now can crop here and we can come on the other side. We find this distance D and we can crop. So now our design diagram is going to be my magenta line, which is the original shear force diagram, just cropped at these ends. And the question is that what is this value VU, which seems to be the maximum value that I have, okay, here, or negative VU here. And how can I find this value? And there are two ways. One is to use geometry. I think the easiest way is to take a free body diagram by making a section exactly here. So kind of building on your statics, what you have now a beam. If I go on that side, you have a beam. So you have your reaction here that is WUL over 2. You have some distributed load. That would be your WU. And you have here your forces. You have your N. You have your shear force V, which is your VU here, and you have some moment M. Okay. And if you take, in this distance, obviously, this distance is D. And if you take now the sum of the forces in the y direction, so you take the sum of the forces in the y direction should be equal to 0, then you have your essentially VU to be equal to WUL over 2 minus WU. This is what you times L. This is what you would end up with, and that would give me your VU to be equal to WU times here L over 2 minus L, and oops, sorry, times D here, not L, WU D. Okay, this distance is D, so you have here L2 minus D. And if you substitute some numbers, what you would have VU equals this WU, which is unknown, and L is 10 feet. So you have 10 feet over 2, and D is, let me see, it's 10.25 inches. So you have 10.25 inches, and you need to you can mention that to 1 inch is essentially 1/12 of a foot. So you have here 12 inches over feet, and you end up with VU being equal to essentially WU times 4.146 feet. And now what you did here, you associated your WU, the ultimate load, with the shear demand. And now if I'm going to write those like kind of nicely one below the other, probably I should move those somewhere here. So I have that, and now I can essentially set my demand equal to the capacity, right? Like the requirement for each design is to have let me just write here, setting demand equal to capacity. And the design requirement, here is that phi VN is always larger or equal than VU, and the limiting case is phi VN equals VU, and in this case here you have 8.75 kips should be equal to WU times 4.146 feet. And what you get here, you get that WU equals 2.108 kips over feet. And this is now your solution. This is the maximum uniform distributed load that this beam can take before you see failure in shear.